Good afternoon, all. Just now 3 o'clock. This is Ralph Schmidt-Peterson. I am the director of the New Mexico Interstate Stream Commission, and I'm here today with Ms. Ann Tillery, who will be giving us a presentation that is the third in a series of webinars that the New Mexico Bureau of Geology and Mineral Resources at New Mexico Tech has been spearheading with a number of research experts across the state of New Mexico for the Interstate Stream Commission, starting with a big picture overview that Dr. Nelia Dunbar gave on July 21st, a presentation on Tuesday of this week by the state climatologist, Dave Dubois, on climate change modeling and what the expectations would be for temperature within New Mexico and a number of other things on precipitation. And today we're here with Ms. Tillery, Ann Tillery, talking about where she'll present on landscape change, fire, and erosion in that look ahead view going out 50 years. Ms. Tillery will say a few things about herself at the beginning of her part of the presentation. Just want to say thank you very much for volunteering to help with the Bureau of Geology and Mineral Resources in this. Ann works for the United States Geological Survey. She's got 20 years or so experience within New Mexico on a lot of these issues, and we're really happy to have her give this presentation today and be part of this team. With that, Ann, would you mind moving the slides, and I'll just say a couple of things about the overall process and then hand it off to you. So first piece for the overall group here again, and John Mumm did this on Tuesday, and I did it on July 21st, but I want to kind of step back and take a look at the big picture of what we're trying to do with the 50-year water plan. And at its largest level, we're seeking engagement from experts and stakeholders with their expertise from across New Mexico about not just the climate change piece, but also how New Mexicans are adapting and dealing with climate change today, and how they do that and how they perceive their level of resilience. So in order to do that, we have the Science Foundation, which is all part of this climate change leap ahead to 2070 that we're talking about today. And really all the webinars through August will do that. Next, we have, and this will start in early September, is this engagement about resilience. How do you all, listening to this presentation today and the others, perceive the change that is being described by the experts? Are you concerned about that? If so, how? If not, how and why? And then for the physical resources that are affected by water that you value the most or value just generally, how resilient do you think you are? How resilient do you think they are? We're doing outreach starting in September 1st in this regard. And then later in the year, we'll be talking adaptation strategies, what people have done to adapt that's worked for them, what hasn't. And then additionally, for areas where there's gaps, recommendations and input about ways to adapt to address those gaps. And then finally, in the spring of next year, we'll be talking about policy recommendations, issues with land management projects, ideas for local decision makers, and research. Next slide. So, just another little bit of a pointer piece on this. Here we are in August. We have 10 webinars. This is the second being conducted in August. There are a couple more scheduled for next week. In September, we'll be talking again, September 1, about the webinar on resilience, and then we'll have additional webinars that come out after that that talk about assessing and self-assessing for resiliency. And then I just want to mention that broadly on a parallel path to this, we'll be having a tribal and Pueblo outreach and communication effort. Next slide. With regards to information about the 50-year water plan, as we go forward, want to point out a couple of different things, or three here for you. First, at the top of the slide, our website for the Office of the State Engineer, ISC, under Hot Topics, has a 50-year water plan page on it. The link is on here, but you can go to our page and pull that up to find information on the plan and the progress and where we're going. Also links to upcoming webinars. Then the second item down below is where we're seeking to incorporate comment from public and stakeholders about what they're hearing. And this is a place we really want you to go if you have comments and thoughts or questions relative to these webinars. So we have one place that we're really trying to document all those pieces. I will say we will be doing that also today through the chat function on this webinar. And in the chat, you'll see a note from myself that, as we go along and as Ms. Tillery goes through her presentation, if you have questions, please type them in here. Send them to me or send them to the audience. It's up to you. And at the end of the presentation, we'll go through, I'll read them out, and then Ms. Tillery will answer those questions. We'll document that here on the webcast, and we'll also save the chat. Finally, if you're having difficulty, negotiating or finding information, the email address at the very bottom of this slide for the New Mexico Water Planning at ISC is a place to go, and we'll be responsive there and help direct you to find additional information. Next slide. So with this, I will hand off to Ann Tillery, and her talk again is about landscape changes and erosion, and it's a part of a long series. Ann?
Yeah, thanks very much. Can you hear me okay?
I can hear you fine.
Great. Thank you, Rolf. And welcome everybody. Thank you for calling in for this presentation. It's nice to have such a good group of people showing up. I'm going to start the presentation by just giving a little bit of background, general background about the assessment that we're putting together, that the panel's putting together, and then I'll move into my part of it. But yeah, this is a collaboration between the New Mexico Bureau of Geology and Mineral Resources and the Interstate Stream Commission with the Office of the State Engineer. And our task is to put together this assessment of impacts of climate on New Mexico water resources over the next 50 years. And so these slides, we're putting them in the front of most of these talks just to explain why this is needed. New Mexico's climate is warming. So a new 50-year plan that the state would put together, it needs to account for the future changes in our climate and water resources reliably. So this graph here on the top in the red is temperature, on the bottom in the blue is precipitation. And temperature, what you're looking at, each one of these dots is an annual average of all the observed temperature readings across New Mexico, and it ranges between the low and upper 50s. And then these horizontal lines going across, those are 10-year averages, just to help point out that in the last several decades, each decade's been warmer than the previous one. And we're at a point now where we're warmer really than what New Mexico has been in the past since 1930. But if you look at the precipitation, it's a little harder to see any kind of a trend. We're still in the range of what we've seen in the past. So a trend in precip is still up in the air. It looks like it's been pretty stable, even though there is some variability. So that's why we're doing this study. And then this picture here, the gold line here is the same exact observed annual temperature that we just showed, but they're trying to forecast where it might end up in the next 50 years. And so surrounding the temperature observations is the emissions models. And these are just a couple of different emissions models that have been chosen for illustrative purposes, but we don't know exactly where the temperature is going to go. It depends on what ends up happening with emissions. So when the panel got together to think about how climate change is impacting New Mexico's water resources, they came up with a list, or we came up with a list of different things to think about, including things like stream flow and recharge. They might be lower, right, because it's going to be more arid, greater interannual variability in precipitation going forward, hotter, more severe droughts, decreasing snowpack. If it's going to get warmer, the precip will probably switch from snow to more rain, which would mean earlier and diminishing snowmelt runoff, a greater demands on groundwater because of less availability of surface water, vegetation stresses, which you've probably seen if you've driven in the northern part of the state with the pine tree kill-off, increasing catastrophic forest fires, which if you've been here for the past 15 or even 10 years, you've seen that, increasing flooding, sediment transport, irreversible damage to soils through loss of vegetation and erosion, and degraded quality of surface waters. So, oops, sorry. So the ground rules for the panel for the study was to assess and synthesize recent scientific literature on climate, hydrology, and impacts of these changes in New Mexico. So we didn't do any new research, but we looked at the body of work in and across New Mexico and nearby areas to put together this assessment. And there were 8 main chapters that are shown here, and the one that I worked on was landscape change, fires, and erosion, and that's what I'm going to be talking about today. This is just the list of panelists, which is I'm probably the greenest one on this list with maybe 20 years of experience in New Mexico, but I would say that most of the other people on this list have 30, 40, maybe even more years of experience. So we're looking at a combined a combined knowledge of 250 years or something like that. It's a really great group, and I'm honored to be a member of it. And as Rolf said, I work for the U.S. Geological Survey. I sit here in Albuquerque with the New Mexico Water Science Center, where I'm a surface system specialist. So I'm a geomorphologist by trade, and I also do a lot of surface water hydraulics, like looking at how surface floodwaters move across the surface. Okay, and the process for putting together this assessment, in February and June, the panel met over Zoom, of course, and discussed the different chapters' focuses. 11 chapters ended up being written by the individual authors or teams of people together, and then we all reviewed each other's chapters. So there was an internal review. In July, it was sent out to 5 scientists who are doing an external review. And in August, we're doing, as Rolf said, these outreach like this one. And also later this month, we should get the external reviews back, and we can start working on addressing and incorporating those comments. In September, we should have the report ready to go out for public comment period. And after a month or so, we will work on addressing and incorporating those comments and having the report finished. So that's the background. And now into my story here. Landscape change, fire, and erosion. I worked on this chapter with Leslie McFadden, who's a soils geomorphologist, emeritus professor from UNM, and Craig Allen, who's also with the USGS and recently retired after 40-some years doing research in the northern part of the state. So I just kind of wanted to start this talk by getting folks in the geomorph brain a little bit with this slide here. So just thinking about the fact that landscapes are attached to climate, they're linked to climate, they're affected by climate, and I think this is something that most people probably are aware of, but maybe don't think about it too much. So if you could just look at these 3 landscapes and just imagine you're looking at a silhouette of them where you can't see the vegetation, you could still tell something about the climate that they have experienced through time, just by the shape of the land. So for example, on the top picture, you see these retreating cliffs and jagged cliffs. On the bottom left, you have, rolling hills. And on the right, you have, pointed mountains. So you know that this is probably experiencing some freeze and thaw type erosion, and it's in a cold, high environment. And likewise, with these rolling hills, there's probably some good soil development, and it's getting a lot more precipitation than someplace like this. So the landscapes are a reflection of the climate. So that's just something to carry with you through this conversation. And then the other thing just to keep in mind, sorry about that, is that landscapes are dynamic, right? They're changing all the time. They change with time, and sometimes they change very rapidly, like when a cliff collapses, and sometimes it's incrementally, like marching dust devils going up the same valley all summer long, year after year, decade after decade, carrying dust with it from one end of the valley to the other. So they're moving. Okay, now this slide, this is from a book called Geomorphic Response to Climate Change that was published in 1991, and it nicely kind of lays out the interrelationships between precipitation, as a result of climate, and processes that happen. So I just want to walk you through this. This will probably be the slowest, most intense figure, but once we get through this, it'll be smooth sailing. So on the left, we have just a very simple flow chart. Climate change leads to vegetation change, leads to landscape change. And on the right, on this plot, we have the passage of time on the x-axis. And then we have these different variables. The stair-step blue line is precipitation. The next green one is vegetation, hill slope plant cover. The red line is aggradation or degradation, and you might not be familiar with those terms, but aggradation is basically deposition of sediment that builds on top of itself and aggrades. So we geomorphologists call it aggradation. And then the black line at the bottom is hill slope denudation rate, or erosion. So and then on the y-axis, we're saying that whichever line you're looking at is increasing if it's higher up, and it's decreasing if it's lower down. So just walking through this story, we're looking at a situation where we had a kind of high level of precipitation that dropped abruptly and then stabilized at a low level. And the next line down is vegetation. So when you have high precipitation, you have lots of vegetation on the hill slopes and in the valleys probably too. And sometime after you lose a lot of precipitation, your vegetation is going to start to decrease. It's going to die off. It's going to change over to a different vegetation type until it stabilizes here somewhere around timestamp G with the new precipitation regime. Okay, now let's look at the hill slope denudation rate, or erosion. When you have a lot of vegetation, you don't have a high rate of erosion because the vegetation serves to increase infiltration and decrease overland flow. But once your vegetation starts to die off, then you start to get a lot of erosion. The erosion increases until some level where the plants start to stabilize. And it is at a high level here, but it starts to decrease again once there's stability in the slopes. And then what's happening in the valley is it's kind of in the middle here between aggradation and degradation, but as the vegetation goes away and the hill slopes start eroding, the valley starts filling up with sediment, and it'll keep filling until the hill slope erosion calms down, and then it'll start calming down, and that's when you can get soil development, because you're not going to get soil development if it's active. So that was a tough one to get through, and thank you for hanging on for that one. Okay, so I want to take that a little closer to home here in New Mexico. This is the results of a study from Steve Renaud up in the Pajarito Plateau. And he was looking at the valley fill in between the mesas on the Pajarito Plateau. So if you look at this upper graph, it's, again, has time on the x-axis, and it has types of precipitation. So it goes back to about 20,000 years ago, which is in the Pleistocene, of course, when it was much cooler, and a lot of the precipitation fell as snowfall. as opposed to rain. And then about 10,000 years ago, we switched to the Holocene, and it warmed up quite a bit. The precipitation regime changed to more rainfall, less snowfall. And down here in plot B, he's plotting up the geomorphic processes. So in this area, in the Pareto Plateau, during the Pleistocene, when it was cooler and more precip fell as snow, it wasn't very active geomorphologically. But at the transition to the Holocene, all of a sudden with more rain, there started to be a lot more erosion, things got a lot more active and kind of stayed that way as it was warmer. So that's a near home example of how the climate led, a change in the climate led to a change in what was happening on the surface. There's another study that was done very similar to this by Mann and Metzler up on the dry Cimarron. I don't have a slide of that because they don't have the same kind of figure, but he actually found, or they found kind of the opposite. Things were much more active during the Pleistocene and quieted down during the Holocene. So it's very difficult to predict exactly what a landscape's going to do. And those two differences in the responses between the Pareto Plateau here and the dry Cimarron illustrate just the variability in landscape response to climate change. And that variability contributes to the challenge in predicting how landscapes are going to respond to any whatever particular perturbation. Okay, I'm going to switch to arroyos. When going through the literature in New Mexico, it just seems like you can't not talk about arroyos when you're talking about geomorphology and sediment. Arroyos have gotten a lot of attention over the years and decades because they are problematic. They cause issues with, loss of land use like grazing and agricultural productivity, and they damage roads and bridges, and they can produce a lot of sediment deposition. That can lead to reducing reservoir lifespans, and they can increase flood hazards because they reduce efficiency of floodplains, and they can drain cienagas. So they're problematic. So people have been looking at arroyos in New Mexico for a long, long time. Going back almost a century, or perhaps even more than a century. I think there's some studies. Right in the center here, we have this pretty well-known study from Kirk Bryan in 1925, where he was attempting to date the trenching of arroyos. And on the right is just a lovely hand-drawn graphic from a 1983 study that shows Chaco Canyon, or the Chaco Arroyo and Chaco Wash. And on the right, on the left, this is a figure from Alan Gillis, 1992, where he's nicely drawn some of the different processes that arroyos go through, with incision, and then they can widen, and then they can start filling up with sediment, and they can incise again, and they can go back and forth between all these things. And in fact, any one arroyo can be doing all of these different things at the same time in different locations. They can be incising upstream, and then a quarter mile downstream, they're filling up with sediments. They're very complex. And this figure, I know that you can't read everything on this figure, but I just wanted to include this to show how complex arroyos are. They're very difficult to predict. So this is a flow chart that I got actually from the New Mexico Bureau of Mines and, Bureau of Geology and Mineral Resources website. It's from a decision makers field guide. And it's just a flow chart summarizing all the possible antecedent conditions, climate, land use factors, and then the adjustments that the streams make that lead to erosion, which is depicted on the orange on the left, or aggradation, which is depicted on the right. So lots of things go into what causes an arroyo to do what it does. But I want to focus in on this middle part here, which is all about climate impacts. So climate variables, of course, are closely related to vegetation, and they're frequently cited as sort of changes in climate, whether it's temperature or types of precipitation, seasonality of precipitation, intensity of precipitation, or amounts, snow versus rain, that kind of thing. Any of those changes, they can perturb an arroyo system, leading to sort of activation of the system, onset of erosion or deposition. Hard to say what it'll do, or where it will do it, but these are perturbations of the system. Okay, and now I'm going to move to sort of what I've been calling accelerated erosion. This is a picture from the community of Mogollon down in the Gila, and this is following the Whitewater Baldy fire from 2012. Of course, that burned 300,000 acres. Still to this day, the biggest fire in the state's history. Thank goodness that we haven't had a bigger one. And then if you'll recall, if you've been here since 2013, in September of 2013, the whole Southwest was covered by this super wet air mass. And for a 3-week period, you can see a huge majority of the state got, or portion of the state got 400 to over 600% of the normal precipitation. And this also happened in Colorado. There was, I think, a number of fatalities from a landslide, and in Arizona, it was a huge, huge system. And after the Whitewater Baldy fire, we installed some rain gauges as part of an early warning system. And during this week, one of the rain gauges measured 7.5 inches of rain, and that was over a 10-hour period, and a max 30-minute intensity of 4.25 inches, and that was on the September 14th. So that's a crazy amount of rain for New Mexico. That's like the equivalent of a 1,000-year rainstorm. And this erosion that I'm showing here, this is the road that goes from Glenwood up to Whitewater Creek. And this erosion, it was a result of that night of rain, but this is not even in a burned area. This is in an unburned area. And this is also another tributary to that same, to Whitewater Creek down there on the unburned side. And most of this erosion was caused by debris flows. Again, this is a, oops, let's see, sorry about that. This is a unburned hill slope here, and these are fresh debris flow scarps. We hiked up to the top of them. They just started by a slip that was maybe 1.5 to 2 feet deep, and it just gained momentum and picked up material. And this is what happened all over the landscape out there, probably on that same night. And it just so happens that aerial photography had been flown in this area right before the fire, and then it was reflown right after this rainstorm. So we were able to look at before and after aerial photography and map out all of the debris flow, the locations where they started, and then also the scarps for a large area around the Whitewater Creek watershed. So this is where we are in New Mexico, down south, outside of Silver City, near the state line. This is the San Francisco River, this boundary here. This is Glenwood, New Mexico. And this is the Whitewater Creek watershed. And then if you're not familiar with these kinds of maps, what we're looking at is burn severity for the Whitewater Baldy burn scar. So, you know, red or orange is going to be the high severity. Yellow is moderate, and then, or orange is moderate, yellow is low, green is unchanged. So this is the edge of the burn scar. You can see part of the watershed was unburned, part was burned. And using this method with the aerial photos, we were able to pinpoint 688 total debris flow initiation points in the area around the burn scar, focused on these rain gauges where we had data. And 352 of them were in the Whitewater Creek watershed alone. So I did a very rough sort of back of the envelope estimate of sediment mobilized. And this is just to give you a feel. This is not a published number or anything like that. But if we look at all of the lengths of all the debris flows that were mapped and multiplied that by a sort of an average cross-sectional area, we came up with an estimate of 1.6 million cubic feet of sediment that was mobilized that night, that came off of the hill slopes. And probably really in a 30-minute period it all happened, but you know, we can't verify that. And if you're having a hard time figuring, like getting your head around 1.6 million cubic feet, it would be enough sediment to fill a freight train 3.8 miles long. Or you could also look at it, oh my goodness, sorry. You could also look at it as enough sediment to erode the entire 53-kilometer watershed down by 0.04 inches. So again, that's just a very, very rough estimate. Like I said, back of the envelope, but it mobilized a lot of material that the DOT and the locals had to go out there and start pushing out of the way with bulldozers. And, you know, this sediment is going to be moving for a long time now. I mean, we're not saying anything about where it's going to end up. We just know it unzipped and got flowing, and now it's kind of going to be moving around for a long time to come and in the way. So sort of closing up this little story here, the number of new channels and scarps cut into the freshly burned mountains and also the unburned areas have really altered the landscape in ways that are going to be probably long lasting, such as destabilizing those hill slope soils. So wherever you get, you know, a scarp, then you've removed all your soils and you've removed the vegetation there, and it's going to be harder for vegetation to get reestablished in there. Also decreasing the length of the overland flow paths. So now that you have these channels cut down on the sides of the hill slopes, instead of overland flow kind of going across the mountain, it'll channelize into these channels, which means there'll be less infiltration, which is not good for vegetation, and also faster runoff. So it could, you know, pick up more sediment. So increasing, that's my third bullet, increasing runoff and sediment supplies to downstream channels. So it's kind of, like I said, it unzipped a system that's going to keep producing sediment and rearranging sediment for a long time to come. This effect could last for years or even decades, and it demonstrates the importance of these rare events. I mean, this was like I said, roughly 1,000-year rainstorm event in shaping sensitive landscapes. And when I say sensitive, I mean maybe weaker bedrock types. You know, this is here in the Gila, it's loosely cemented volcanic conglomerate. So some landscapes are going to be more sensitive because of the rock type, and others are going to be less sensitive. Okay, and then just one more case study from the Las Conchas fire in northern New Mexico. This was in 2011. I'm sure if you've been around, you remember the damage to the Dixon apple orchard. That's what this picture is from. And there have been quite a few studies at this point now that have shown that rain falling on areas burned by wildfires can produce stream peak discharges orders of magnitude. We're talking, you know, up to 870-fold beyond the typical values seen in systems with fully vegetated conditions. Okay, so here's just a map showing this big outline is Frijoles Canyon in Bandelier National Monument. There's a stream gauge here by the park headquarters that's been there since the 60s. And then this upper watershed is where we put in a second stream gauge just to provide some early flood warning for the folks that live and work down by the headquarters. And again, we're showing another burn severity map. So this is the border of the Las Conchas fire with the bright red colors showing a high severity area. So big portion of the what we call the neck of that canyon was burned very high severity. Okay, and so there's that stream gauge that's at the headquarters. That's what it used to look like before it got destroyed. And this is what I'm showing here is the annual peak stream flow data. So prior to the fire, for this 45-year period from 1965 to 2010, the green bar here is the mean, the average of all those annual peaks for that 45-year period, and this is in gauge height. So we're looking at, you know, less than 3 feet. And the maximum recorded gauge height for that period was a little bit over 6 feet. And by the way, that was fire related. That was after the 1977 La Mesa fire. For the 6 or 7 year period after the fire that we have on record so far, the annual, the mean of of the annual peaks has gone way up. In fact, the average is higher than the previous max, and the max is just skyrocketed. The maximum recorded gauge height is above 13 feet. So that's an example of what all these studies are showing us. This is what this looks like. If you've been to Bandelier, if you're familiar with this, this is the parking lot, and this is a flash flood in response to what we call just a short duration, high intensity rainfall event, so like a monsoon. And this wasn't even anything like crazy off the charts. It was just like a respectable monsoon storm, like maybe a 2 or 5 year event. It was not certainly something that this area hadn't seen before, but because of the burn severities up the canyon, the stream discharges were just, unlike anything that we've seen since we've been gathering data there. And these are just some very dynamic pictures from up in the canyon, from some floods that happened in 2013. And this right here is a mud line. And there's a person for scale. And over here, same thing. This is a mud line, a barber for scale. And this is scrape marks from, trees and logs that were probably at the front of the flood wave that were scraping across these canyon walls. Okay, and this right here is that stream gauge that I was telling you about that we installed upstream, about 6 miles upstream, in order to give the park some early warning if there was a flood wave coming. And in the summer of 2013, a monsoon rainstorm with a peak 10-minute rainfall intensity of 3.75 inches an hour, it crossed over Frijoles Canyon from north to south. And Frijoles is kind of east-west trending at about 11:30 p.m. on July 25th. And the flood wave that was generated after that rainstorm passed, it instantly triggered an alarm on this gauge of 18 feet. And, I had the alarm set on my phone so that I would get one if it was at 2 feet and 5 feet and 6 feet, and my phone just went bing, 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 bing. They all went off at the same time. So it was a flood wave that was about 18 feet high. In the upper portions of the canyon, these trees that had been left standing where they were killed by the fire 2 years earlier, they were finally knocked over. They were carried downstream and deposited in these giant log jams that were like 20 feet high, and I have a picture, and 50 feet long. And then, shortly after this gauge served to alert the park employees, and 2 months later, there was another big flood associated with that September 2013 wet air mass, and this gauge was irretrievably buried by 7 feet of sediment. We couldn't get it back out, and I have a picture of that. So this is Luke pointing at the tree or the little bush where the high water mark went right through that bush from the July flood. And this is following the September 23rd flood. So this is the same bush here and here, and this is the same junction box here and here. And the gauge is buried forever. It's probably still under there. Now, I'm not sure what's happening today, but a huge amount of sediment came down. It just paved a highway 7 feet deep at that location. And then when it was smooth, it was like a smooth roadway. So every subsequent flood that came down for a while then just raced down the canyon because it had this nice highway to flow down. And increased burn severity. So this is a picture of an area that was burned severely. Every tree is dead. Increased burn severity enhances the propensity for and magnitude of surface runoff generation. This has been well documented. And warming temperature leads to more, larger, and hotter wildfires. And this has also been well studied. So as it gets warmer, we're looking at having more severe, hot, severe, where it kills everything, type fires, which do tend to lead to worse erosion. And just to demonstrate the connection visually between wildfire frequency and temperature, I wanted to show this. This is a study out of Yellowstone by Grant Meyer and Jen Pierce, but they also did something similar down, well, Grant Meyer and Jed Frechette did something down in the Sacramentos in New Mexico, but it doesn't have as long as a period record. So I wanted to show this. Again, we have time across the x-axis. It starts here as present, and way to the left is 12,000 years going back. The red line, 12,000 years. The red line is fire activity, and they put this record together by looking at these debris flow deposits that have been left behind by fire, and they could find charcoal in them, and they could date it. So they looked through all these debris flow deposits and dated all the charcoal and could figure out when these fires happened, how many happened when, and they rebuilt a fire history like that. And you can see that the fire history has highs and lows, it goes up and down. And what he's plotted on top of this is these blue lines. Those are the North Atlantic minimum temperatures. And you can see quite clearly that when the temperature's at a minimum, the fire frequency is less. It goes down, and it goes up in the warm areas in between. At the very end, he's plotted the Little Ice Age, which is a cool period, and you can see there's less fire activity, and the Medieval Warm period, which is warmer and there's more activity. So they're definitely linked. We can expect to have more bigger wildfires, and that's well established. Let's see here. Okay, and just a couple of closing thoughts. Loss of vegetation due to reasons other than wildfire, like, drought, die-off, disease, pests, even anthropogenic reasons like grazing or human alterations can also lead to these similar accelerated landscape change. The second point here is that, rain is more erosive than snow. So if our precipitation is, as it gets warmer, we're gonna shift from snow to rain, you can just expect that will increase erosion somewhat. And the third bullet is it's very difficult, not really feasible to predict how every setting in the state's going to respond to climate change. That's a tall task, but we can say that a change in temperature and precipitation patterns will likely lead to a direct response of some kind, especially in sensitive landscapes throughout New Mexico. And that's all I have prepared. This is a picture of one of those log jams that I talked about, and here's Brian for scale. So thank you.
And thank you, Anne. And I want to say thanks very much for the presentation, and for members of the audience that have questions, please add them into the chat. And as we were going along, I did that myself, so I thought I'd maybe start out on a couple of those for you, Anne. And part of it has to do with my experience as a water resource manager, on the river in the Rio Grande, and realized that back in the 1920s through 1950s, the Rio Grande, really from almost Espanola, New Mexico, down past El Paso, was realigned and excavated out by various federal agencies due to sediment inflow that had come in from droughts, maybe in the late 1800s and so on, and caused really significant problems in the Middle Rio Grande Valley for flooding, down in the El Paso area, and really made it difficult to irrigate for decades. And so the first question there is, for the leap ahead analysis work that's done, does it give insight into maybe a change in the amount of sediment excavation work that New Mexico or New Mexicans should expect and will need to get prepared for, from areas that have been burned, or just maybe have lost vegetation due to climate change?
Does it give an estimate of how much we'd be looking at?
Yeah, I think
it doesn't have that.
Yeah, or insight into that thing about a change piece. I'll just have a little conversation here amongst the two of us that others can't engage in, but with this format. But there's millions of dollars spent even today per year, kind of moving sediment out of arroyos or roadways and trying to maintain those roadways, and also just to maintain a flowing river in many places. We wonder with climate change or and other pieces, should we expect that rate to increase maybe through the peer-reviewed work?
Yeah, I mean, that's my conclusion, is that if, in the past, when we've experienced, when the landscapes have experienced a change in the precipitation regime or whatever, they've gotten activated, and it's hard to know what that'll look like, but it moves sediments moving from one place to another, and so there's a lot more stuff moving around, getting in the way, obstructing things. Then when you have stable conditions for a long period of time, things can kind of settle down. So yeah, that I do try to make that point in this chapter, that I do think a lot more stuff is going to be moving around, and some of the issues could be filling up of reservoirs or problems with road crossings and things like that. But do try to make that point. I don't have an estimate of volume or anything like that.
Okay, no, thank you. But that's helpful too, in the context of like what we're kind of planning for. Was thinking about differences in settlement yield, and then the next question really was about more of a water yield type of a question. Looking at the graphic that you showed of pre-fire gauge heights and post-fire gauge heights up through 2017, and the question really was how long do these higher type flows last after a catastrophic fire? 3 years, 5 years, more? Does it change the volume?
That's a really good question. That's the question that we get asked all the time, and there have been different numbers that have gone out. 3 years is a common number that goes out, 3 to 5 years. But obviously, it's highly variable, and it depends a lot on the type of precipitation you get following an event like this. Because if you get a couple of years of nice gentle rainstorms without any big monsoon storms, you can get some vegetation coming back, and then you're kind of in the clear a little bit. But if you get crazy rainstorms, then it just keeps causing more damage, and it's harder for the vegetation to get established. So it depends. The answer is it depends to some degree. I don't think, I mean, I actually try to kind of avoid using the word recovery, because in a situation like this where all the forest is completely killed, it's not going to probably ever go back right to exactly the way it was. It's going to assume a new normal. And as far as the yield goes, like groundwater recharge, is that what you're thinking of? Or
yes,
that's another really good question.
Yeah, recharge or just generally, the amount of volume of flow. You see a gauge height piece come up there, and the thought would be, oh, that's a lot more water. But the question would be, really, is it really? And if so, for how long?
Yeah, well, probably, in the 3 to 5 year range, it might be really high like that before it starts to go back down again. It may not ever go back down as low as it was. And that kind of flow just comes through the system super fast. That's just a gauge height. So it's a super fast peak on these types of floods, and then it goes back down again. And it's probably not great quality. It's filled up with sediment and silt and charcoal and stuff like that, and you're getting a lot less infiltration, so less recharge.
Okay, thank you. And one more, I'm looking to see on the chat. Haven't seen any more come up here, and I'm hoping that that's not something that I've not got right in my viewing of these questions and stuff. But I did have one more that I wanted to ask. And so these the examples that you've been showing, were from catastrophic fire, extreme precipitation, which from my read of what we've seen so far with Leap Ahead is that type of variability and change is what we should be expecting more of. You know, could these same types of flood flows happen in areas that aren't mountainous after a fire, or in other
Oh,
cases?
that's a really good question. I wouldn't think, I mean, it depends. You'd have to have some kind of a little bit of a slope, but I think that, yeah, even in low areas, gradual areas, it probably won't be as the same kind of velocity. You know, it won't be as erosive, but yeah, you could probably still get a lot of flooding, you know, with that kind of rain in low, or when I say low, I just mean like flat areas, but probably not as erosive, not damaging in the same kind of way.
Okay. Well, thank you. I don't see any other questions, and so unless somebody else has something in the chat or can send me a text or something saying, "Hey, Rolf, you're not getting
No,
this
I
right."
don't see any either.
Yeah,
And well, wait a minute here. Oh yeah, these must be your questions.
they are.
Yeah, I don't know. Maybe
All
the
right.
chat's turned off, but I'm
Yeah.
okay with that.
All right. Well, thank you very much for the presentation, and I very much appreciate it, and also appreciate all the attendees. Look forward to you all joining us for the next webinar next week. Thank you very much.
Yeah, you're welcome. Thank you.
Take care.